Yes, thank you. Good. Now, 3.7 is now the final chapter of the stress. And this gives you a graphical solution as an alternative solution method, as an alternative to the linear algebra solution for calculating eigenvalues and eigenvectors, actually. I understand that many of you have seen the circle of Mohr already, maybe not all of you, so I will show it in my words again and also with our conventions, which might be slightly different from that what you have seen before, or it's the same. Now, consider the following special stress, and that one we now have values on the diagonal, sigma 1, 1, sigma 2, 2, sigma 3, 3. As usual, we have one shear stress component, and we do not have values on the other non-diagonal elements. Okay, so this is a special stress state, and that one is relevant, for example, in a long bar. It is also relevant, for example, in a dam, the dams which are saving Netherlands from the ocean water. So if 3 is the long direction of the dam, along the dam, then the stress state inside the dam can be, in most cases, described by a stress tensor which has these components, but not those. Okay, so it is not completely irrelevant. Now, the disadvantage of the Mohr circle is it only works for such stress states. So with other words, when you have the zeros on the non-diagonal and you have a 0 here, that is included in this special case. It doesn't have to be 0, 3, 3. Sigma 3, 3 doesn't have to be 0. Okay, so the Mohr circle works in a two-dimensional subspace, but that one is only allowed to process if here are really zeros on the non-diagonal. Okay. Sigma 2, 1 equals sigma 1, 2. We proved that this is in mechanical equilibrium due to moment equilibrium. Okay, and sigma 3, 3, this is actually a hint for you. If you have a stress tensor like this, then sigma 3, 3 must be a principal stress because there are no shear stresses on the 3 plane. Sigma 1, 3 equals sigma 3, 1 equals 0, sigma 2, 3 equals sigma 3, 2 equals 0. That means sigma 3, 3 is already a principal stress, but only if you have the zeros here. Remember, principal stress, we obtained the principal stresses by bringing the stress vector on a side, on a face of the cube, parallel to the normal vector. So by rotation, we remove shear stresses. So principal stresses are pure normal stresses without shear stresses. And this is what is reflected here, just as a repetition of what I said already. And in the exam, this is useful because if we give you a stress tensor like this, then you have already one answer for the principal stress. One eigenvalue is given, can be observed, can be read off directly. Okay, now the linear algebra way of calculating the principal stresses, this is the repetition and rewriting at the same time, is taking the determinant of the stress tensor minus the sigma, which is the unknown which we want to find, and the zeros we take from the example case above. Okay, the characteristic equation then has a sigma 3, 3 minus sigma, which is coming from here, and it has a quadratic term which is coming from the subspace, from the two-dimensional subspace tensor. Okay, now when you see this is a third-order polynomial, but it's already decomposed in the first order and in the second-order polynomial. If you have something like this, do never multiply out these things. You don't need to do that unless we ask you to calculate the invariance. For the stress eigenvalue calculation, this form is much better because it allows you to read off one eigenvalue of stress must be sigma 3, 3, because then the equation is 0. And then drop it and compute the second order polynomial stress. Okay, now this term inside the second order polynomial we want to multiply out and rearrange a bit. So multiply it out and rearrange it according to the power of sigma. Sigma 2 is the largest power, sigma to the power 1 is the smallest, with the prefactor sigma 1, 1 plus sigma 2, 2, and sigma 1, 1, 2, 2 minus sigma 1, 2 square. This is the constant with sigma to the power 0. So according to power arranged. And this is repeating the equation from the previous slide. This first order polynomial has answer sigma 33, that is we put at the back, at the bottom. And the second order polynomial, this is the solution to the second order polynomial. So the sigma 1, 1 plus sigma 2, 2 goes here, outside of the square root, and inside of the square root also, minus 4 times the constant times the prefactor, and the prefactor is 1. Okay, so the 4 comes from the solution equation. And this one we can combine together, and then we get something which is sigma 1, 1 minus sigma 2, 2, sigma 1, 1 plus sigma 2, 2, and a lonely sigma 1, 2 square here. Okay, so this is the solution to the eigenvalues using the polynomial solution equation. I hope you have seen that one before. Okay, the order, since it's symbolic, we don't know which one of the eigenvalues is the biggest one. Probably the plus and the minus tell us something, that the plus gives us a bigger one than the minus, but the sigma 33 can be anywhere in between, or outside, or larger or smaller. Okay, now this was the eigenvalue calculation. They are not ordered. The eigenvector calculation is doing the same thing again. We take one of the eigenvalues, insert it on the diagonal, minus the eigenvalue, and then we have to solve this equation system, find the n1, n2, and 3. Okay, now doing this, I don't want to do this into too much detail. This is now doing symbolically what some of you or most of you have done already in some of the exercises. Now, you never have to use numbers. You always can work with symbols. So here we do it symbolically. I want to show you that one once at least. And the n1 eigenvector is designated as a1, a2. The n2 eigenvector is designated as a2 minus a1, such that it is perpendicular to that one. And we know that the 3 components must be 0 because the n3 eigenvector must be pointing completely in the 3 direction and nothing else. So from this tensor, I can immediately see n3. So that one, what you have to keep in mind. So in the exam, from this special stress, you get eigenvalue for 3. The sigma 33 component is one of the eigenvalues, and you also get the 3 eigenvector for 3. It must be pointing in the 3 direction. Okay. Now, if that is the case, then n1 and n2 must not point in the 3 direction. So we have only 2 unknown components for n1 and 2 unknown components for n2. And since n1 and n2 must be perpendicular to each other, they must follow this relation. Convince yourself, a1 times a2. Take the inner product of n1 and n2, a1, a2, plus a2 times minus a1 gives us 0. Okay. Furthermore, n1 must be normalized. This is written here. a1, a2. And when we now take all this, insert it, or look into the equation system, the complete equation system, then we get relations for a1. Namely, a1 should be proportional to sigma 1, 2, divided by a constant, a coefficient. A2 should be sigma I minus sigma 1 divided by the same, and W is just an abbreviation for that is what we have in the square root here. So this is the symbolic way to solve for eigenvectors, to find eigenvectors. And actually, when you do this, then you will find a rotation matrix which is related to rotation around a certain angle. But I first wanted to say something else here. The sigma, how do we get this? The sigma 1, 1, 2, A1. So N1, A1, sigma 1, 2 comes from here or from here. So take the second row, sigma 2, 1 equals sigma 1, 2. Sigma 1, 2 times n1 gives you one of those relations. The other one, sigma 2, 2 minus sigma I times n2 gives you something which is not exactly this one. The sigma 1, 1 minus I n1 gives you this relation here. Okay, and this one comes from the normalization. They must fulfill, the two components must fulfill the normalization condition, and this is why we always get a square root from normalization. Okay, now n3 is pointing in 3 direction, and 2 and 1 are somewhere in the 1, 2 plane. So that corresponds to a rotation around the 3 direction, and this is what is written here. So the transformation matrix, the rotation matrix, is a 3 direction, and we are living in the 2-dimensional subspace, and cosine alpha sinus alpha is in principle what I showed before. Only on my sketch I was rotating around the 2 direction. Here you can do the same thing, rotating around the 3 direction, and then the cosine alpha sin alpha are in the 1, 2 subspace and not in the 1, 3 subspace, as I showed in my example. I hope that is clear. Now, again, we use the transformation of stress, as we have done already several times. The new stress tensor, when we rotate around the 3 direction, it doesn't change the 3, 3 component. It will change the 1, 1, 1, 2, 2, and 1, 2 components. So those will be changed if we apply the transformation rule to the stress tensor. Okay, so this is the symbolic short notation. This is the lengthy notation, and this one, all these calculations, matrix multiplication, you have to carry out. And if you do this, you get sigma for the normal stress for the direction alpha, and tau, the shear stress, in the direction of alpha, of rotation around alpha. Okay, and this is a lengthy calculation. I will not do this on whiteboard, that would take forever. I leave this to you. Take this, make sure that you have understood where the matrix comes from. The matrix, I have shown you how to build it. Take the matrix multiplication and practice yourself, and you should arrive at these equations. Now, the visualization, rotation around the 3 directions, so we take it out of the plane. The 1 is horizontal, as I did in my sketch. The 2 is vertical. I had a 3 here. So you always have to be careful and read what direction we want to rotate about. It can be in all 3 directions. Okay, and we rotate around 3, around an angle alpha. And this is practically what I did with only swapping 2 and 3. Okay, this is the stress cube in the original coordinate system. This is the plane I'm interested in the new coordinate system, and sigma is the normal stress, tau is the shear stress. Sigma is the normal stress, the lengthy equation, tau is the shear stress, almost as long. Okay, so this is the geometric graphical interpretation of that, what the transformation of stress around rotation around angle alpha is doing. Now, when we take these two equations for sigma and tau, then you actually can rewrite that one, and you get something which sigma alpha minus something squared plus tau alpha squared equals something on the right hand side. Okay, this is the equation for a circle. I don't know how you describe in mathematics, how you in your high school mathematics was describing a circle. In my case, we were describing the circle as x square plus y square equals radius square. Okay, so if you remember your high school mathematics, a circle is one coordinate squared plus the other coordinate squared equals to radius squared. Okay, and this is Pythagoras again, the Pythagoras which I sketched you on the whiteboard. Before, we had p square on the right hand side equals tau square plus sigma square. I swapped to the whiteboard. again, yes, here. We had p square equals sigma square plus tau square. This is what this equation means. It's a Pythagoras. And we are allowing to have arbitrary angle here. So one angle must always be rectangular. The other angles we can change. And now we were using alpha for the angle here, alpha. Good. Having said this, if you have a circle, you can plot one. And what are the characteristics of the circle? How can you plot a circle? You first need the midpoint, M. What is the midpoint? If we identify the first square with the horizontal axis, then the midpoint is what we subtract here. So the 1/2 sigma 1, 1 plus sigma 2, 2. This is the midpoint, and it is on the horizontal axis, not on the vertical axis. That's why the vertical value must be 0. So the point M is on the horizontal axis with no offset in the vertical direction. Okay, so on the horizontal axis, we plot the normal stresses, sigma. Okay, so when we ask you to plot the Mohr circle, first plot the axis, normal stress, then plot the midpoint. You can read that off from the stress directly. Okay, and then what next? If you remember well the equation of the circle, then this is the radius squared on the right-hand side. So we just take the right-hand side, take the square root thereof, and that gives us the radius. Okay, so next, after the midpoint, we plot the radius, and we are finished already with the circle. Okay, for 0, if alpha equals 0, point A is representing the sigma 1, 1 component and the sigma 1, 2 component. And this is now, again, convention. We decide to plot the shear stresses in the negative direction, not in the positive direction, such that the rotation has a certain meaning. If we would, and in some books they do, plot the shear stresses upwards, then the order of rotation, clockwise versus counterclockwise, would be exchanged. So we want to have this rotation direction. So we have as convention sigma to the right, normal stresses to the right, shear stresses to the bottom, not to the top. Okay, in 1 or 2 examples, we do it oppositely such that you see it once. In the exam, if you choose to do it differently because you practice based on a different book, different lecture material, that's also acceptable, but you must clearly indicate that you use the other convention, and you must clearly interpret all your angles in the opposite sense. Okay, so this is how you make this. This is how I derived the equation for the circle of Mohr. This is how I graphically do it. Now for the circle of Mohr, getting the midpoint, that is relatively easy if you remember this equation, but also when you just follow the rules and plot the normal stresses on the horizontal axis, so sigma 1, 1 here, sigma 2, 2 here, then the midpoint is exactly the point between sigma 1, 1 and sigma 2, 2. Okay, so there are 2 or 3 ways to remember the midpoint. The radius is a little bit more difficult to remember, but graphically, when you take the midpoint, sigma 1, 1, and the shear stress, then you again have a triangle, and this is the triangle which I showed you in my word board. This is the Pythagoras. Radius square equals shear stress components squared, and the distance from sigma 1, 1 to the midpoint. Okay, so digest this graphically. You will practice this in a few examples. And one possible exam question is always, given stress tensor, calculate the circle of Mohr. Not calculate, sorry. Sketch the circle of Mohr. Now, point A is here. Point B is opposite direction. And that's in the circle of Mohr, that is 180 degrees or pi. Whereas here, the angle alpha corresponds to pi half. So this half needs an explanation. I will come back to that in a minute. So that's the only thing which you cannot understand in the moment. A, the point A consists of the first normal stress and the 1,2 shear stress. Point B corresponds to the second normal stress and the 2,1 shear stress. Okay, so we have now the axis. Always important to plot the axis. Indicate what you are plotting, normal stress, shear stress. Shear stress goes down. Then take the midpoint, take the radius, and plot the circle. Take the components, sketch them, take the shear components, and you can indicate point A and B. Now, what is missing is point C, D, E, and something else. I show on the next slide. Okay, what is C? C is a stress in an arbitrary angle 2 alpha. C is the stress in stress space, in real space, or oriented around alpha. In the Mohr space, we rotate around 2 alpha. Okay, I will explain in a minute again why that, how I remember that it must be 2 here. From the mathematics, it follows. It follows from the equations here. Okay, now point D is the rightmost point on the circle on the horizontal axis. Point E is the leftmost point on the. So those are easier to interpret than point C. I will come back to point C in a minute. What is point D? Point D is the maximum normal stress this circle experiences. You remember, maximum normal stress means it's an eigenvalue. It's the maximum eigenvalue. This is the minimum normal stress. So that is the minimum eigenvalue in this two-dimensional subspace. So point D on the circle gives you now a graphical value, a graphical approximated value of the maximum larger eigenvalue. And point E gives you the graphical observed value of the smaller eigenvalue. Okay, graphically, after you sketch the circle. Also, you can get this one by taking the midpoint plus the radius, that gives you point D. Taking the midpoint minus the radius gives you point E. And this is mathematically exact, whereas the graphically reading off from a bad graphics, that is not exact, clearly. Okay, so the Mohr circle gives you 2 eigenvalues, graphically, approximately, or if you remember midpoint plus radius, then you also get them exactly. Okay, now back to point C. Point C is the one point here which I can get from the equations, and the 2 alpha 1 or 2 alpha, the tangent of 2 alpha corresponds to sigma 1 2 divided by sigma 1 1 minus sigma 2 2. Half. Okay, and that is what I get from the mathematics here, from the circle equation definition. I can read this off. Okay, now to conclude, the principal stresses in the mathematical operation are midpoint plus radius gives you one principal stress. The other one, midpoint minus radius, gives you the other principal stress, and those are exactly the same as we found from the linear algebra calculation. Okay, only this one is easier and shorter. Disadvantage is it works only for this one special stress state. Okay, now almost done with the circle of Mohr. One thing to add is if you have a 3-dimensional circle of Mohr, then you can have 3 possible circles. One corresponds to the first eigenvalue and the second eigenvalue. This was the one which we were just discussing. In the third direction, if the tensor is more complicated, you can have a circle of Mohr between the second and the third eigenvalue, and you can have a circle of Mohr between the first and the third eigenvalue. And now they are sorted. You see sigma 1 is larger than sigma 2 is larger than sigma 3. Okay, so the circle of Mohr, the circles of Mohr describe any stress state in this subspace, and the dashed area now is stress states in other directions, rotating around 10 degrees will give you points in this dashed area. So the beauty of stress living on a circle and not inside the circle, only on the circle, this is only in the two-dimensional subspace as we have defined before. If you have three-dimensional space, then you deviate from the circles, but you cannot get into these inner circles. You cannot get out of the outer circle, but your stress can live in any of the points on the dotted area. Okay, working with three-dimensional Mohr circles is much more advanced, and we don't do it. We don't ask it from you. Just for completeness, I was pointing this out. Now, end of lecture. Next will come strain, but that let's first discuss the circle of Mohr.